Okay, so you're probably thinking, why are we looking at lines? Why are we looking at curves? Why are we looking at functions when I want to solve some real problems? So now we're going to use differentiation to look at some real world applications. So to do this, we're going to just jump straight into our first question in the book. So the question states, a sustainable urban drainage swale, which is a great big pond, is to be made from a square sheet of rubber. So this is our square sheet. Not very square, but anyway, a square sheet of rubber. So with sides half a kilometre long, so we know that side has to be half a kilometre, and that side would have to be a half kilometre. Okay, so the next thing it says is by cutting out a square from each corner and folding up the sides and joining the cut edges, find the maximum volume of the swale. So that would then mean if we were to put a little corner inside and we were to cut these corner squares out, we could fold the rest of this sheet up and we could create a pond. So what potentially we could call that x, and that would have to be a square, so that would be x by x. So now we can make some numbers for the center where we can describe this width here in the center. Perhaps we could describe that as a half minus, or we'd have x on that side, x on this side, so it'd be half minus 2x. And likewise, that would go both ways because this is square. Okay, so that's our description. Now we need to think of some boundaries. So we know what x is, but we need to set some limits maybe for it, what the maximum it can be. So our x, well, it can't be equal to 0 because if it was equal to 0, then we wouldn't have a pond, we'd just have a very flat sheet. And that would probably give us a maximum area, but we wouldn't be able to store anything in it. And then if it was equal to a quarter, that would mean that the volume would be small because this is a half. So it has to be less than a quarter, because otherwise we would have the whole pond would just be folded in two. We'd just be folding the paper in half or folding the rubber in half. Okay, so we've got an expression here. And now we can begin to think of, right, so we're calculating the volume. And the volume is equal to, well, the area, the base here, the area, times by the height. So if we put this into our equation, we can then say that volume is the height, which we're calling this little x here. And then we're going to say our area, which is our half minus 2x squared. So now we have an expression for our volume. So what we've been asked to find is the maximum value. So clearly that states we can maybe do this using differentiation. So we would multiply all this out. So if we say that V equals, we'll tidy it up a bit, that would be a quarter minus 2, 4, should be 2x plus 4x squared. We have to multiply this by x, which would mean we'd have a quarter x minus 2x squared plus 4x cubed. And then we can say that our dv by, this is a real thing, so let's make it a dv by dt by dx equals, where we differentiate this and we get a quarter minus 4x plus 12x squared. Okay, so what we're actually doing here is we have this expression, and if we were to plot it between two lines, well, would be between 0 and a quarter, it would actually begin to look a little bit, so this was 0 and this is a quarter, 1 over 4, it would begin potentially to look like this. So what we're trying to find now is our volume and this is our x. We're trying to find the point where this would be our first turning point, this would be our second turning point, but we want to find the turning point in the middle where we actually have the maximum value. So we can do this. So what we can do now is we can say, well, we've got our differential. and we can begin to solve for x. So if we then put this equal to 0, we would say that equals a quarter minus 4x plus 12x squared. You could stick this in the quadratic rule, but this screams to me, as it's a function of 4, that 0 equals 1. We'll turn this round, so 12 times 4, we multiply it by 4, and we'll get a 48x squared minus 4 times 4 minus 16x plus 1. So let's neaten that up. Then we can solve that quite easily when we say that's 4x minus 1 and 12x minus 1. So therefore, x would have to equal either a quarter or x equals 1 over 12. Okay, so we now have our two values. We can then also do our turning points where we take the next differential of this, where we say that d squared v over dx v squared equals, so we have our 48. So we're actually going to go back to the smaller value here, where we can say that we have our d, so it's a quarter, which doesn't differentiate, minus, which equal minus 4 plus 24x. So now what we can do is we can plug our x values back in, and what we can begin to work out if these are a positive or a negative turning point. So what we can see is if we put in our negative a quarter, we would say that that would be minus 4 plus 4, which is equals 0, which is the quarter times by 4, which is 12 and 6. It would be 4, 4, 8, 12, 16, 24. No, it wouldn't be. It'd be 12. It would be 6, which would be positive 6. So that would be a minimum turning point. So that can't be right because we want to find a maximum turning point. We want to find the least value. So if we put in a 12, where we say that that would be negative 4 plus 12 times by 24, which is 2, we get that equals minus 2. Therefore, that would be a maximum turning point. Therefore, the value for x would have to be equal to 12. Okay, so now we have our original equation all the way back up here, where we can say that v equals x a half minus 2x squared. So we can put that back in. So v, our volume, equals x a half minus 2x squared, which would equal a 12. That would be a half minus 2 times by our our half x squared, our square value goes there, sorry, our values, are minus 2 times 12, and we square that. So then we would get, if we stick all this in our calculator, we would get that that would equal 101 over 108 kilometers, or what you'd probably get in the calculator, that would equal 9259259.25 meters. And to get all the points, that would have to be squared on both of them, because this, no, it wouldn't be able to be cubed because this is a volume. So we've worked out our maximum volume if our sheet was half a kilometer by half a kilometer would be this. So this actually shows how this can be used really for a real world problem. Okay, so we'll do one more example and then we'll leave it at that. So what we can say is, the next question asks, if we had a cylindrical rock core, so maybe you're doing some of Rich Shivrel's work and you're looking at cylindrical rock cores. It says a cylindrical rock core has, I'll draw it here, a radius of r meters, okay, and a height of h meters, okay. The sum of the radius and the height, so radius plus the height, equals 2 meters. Find an expression for the volume in terms of R only. So we want to find the volume in terms of R only, and then we want to find the maximum volume. Okay, so let's see what we've got here. So we've also been given that the volume of the sphere, this will be given in the formula sheet if it is a question of the exam, equals pi r squared h. Okay, so the first thing it asks is we want to find the volume in terms of r only. So this means we're going to have to rearrange this h value here. So we would say that h equals 2 minus r. So we can then stick this back into this equation where the volume equals pi times by r squared multiplied by 2 minus r. So now we have an expression of in r as what it was asked, and we could neaten this up. We could say that would be pi 2r squared minus r cubed, and that would be our expression for v is what we've been asked for as the first part of the question. So it also asks that we want to find the maximum volume. So again, this means that we need to find the turning point. So how do we do this? Well, first of all, we need to take the differential. So we can take the differential of this again. So we can say that dv by dr equals, so it might be better if we have it in this term where we have a pi. So we'd say that's pi r squared. This is multiplied by it, so it does stay. So we can see that we'd have 4r, I'm going to stick our pi on the outside, minus our 3r squared, and this would be our first differential. So that means we could then do a little bit of rearrangement. If we set this equal to 0, we can say this would be r pi multiplied by r minus 3, so it'd be 4 minus 3r, a bit neater, r pi multiplied by our r's come out, so 4 minus 3r, and that then means we could solve for r, so we can find that the radius have to equal either 0 or the radius would have to equal 4 over 3. So straight away, okay, yes, it is going to be a maximum if we have r equals 0, but we can't have a radius that equals to 0 because that's just not physically possible. So all we have here is r equals 4 over 3, which we can check if this is our answer. So then we can say that d squared v by dr squared equals, well, we can then take the second differential here. So that would be then equal to 4 minus 6r, still keeping the pi, and we can then, if we just make it in terms of r, so we're forgetting about this pi because we're setting it towards 0, we want to say that d squared v by dr squared, we get rid of the pi because we're actually solving for r now, and this would equal to 4 minus 6r. And what we need to say is if we stick this 4 over 3 in there, we would get that the answer, if we said that 6 times 4 divided by 3, so 6 times 4, 6 times 6, 12, 18, 24, 24 divided by 24 divided 6 times 24 divided by the same on the bottom, 6, 12, 18, 24, we would get that that actually goes quite nicely when we minus the 4, that would go to -1. So just stick that in your calculator in other terms. So we know that this has to be a maximum turning point because it's for less than 0. Therefore, we can work out our value for the volume, where we can take our original equation where v equals the pi 2r squared minus r cubed, and we can say that would equal pi 2 times by 4 over 3 squared minus 4 over 3 cubed, and that would then equal, if we stick it into the calculator, 2.67 meters, describing a volume again, so that would be cubed. So that's just 2 examples how we can show how differentiation can be quite useful. This has been quite a sparse lecture this week. We haven't had too much information in it Go away and think about these. Try some of the examples because this is something which is quite likely to be on the exam.